So last time we spoke about an example of the deformation quantization in case of Poisson structure. So let me recall you a few details. So if we have a Poisson manifold M pi, pi is a Poisson bivector, then to construct deformation quantization of M is to construct an associative subproduct on the space of all smooth functions on M enhanced by the formal variable h bar, such that, of course, the star product is associative and h bar linear. Okay. Number two, the first few terms of this star product of A and B are given by the formulas A times B plus h bar divided by 2 A comma B. And the remaining part is given by some formal power series of bidifferential operators of A and B. There are two other conditions, more technical, which are sometimes omitted. First, it is that the unit function gives the unit of the product. And also that bk are skew symmetric depending on the on the index. So these two conditions are sometimes omitted, but the first two are observed, always observed. The only thing which people sometimes people just modify this condition number 2 a little bit, replacing it by 2 prime, that the commutator of A and B with respect to the star product is equal to h bar of A and B plus something which is infinitesimal compared to h bar, right? One can show that these two conditions are equivalent. Of course, if you have this formula, then you have this equation, but vice versa is not so evident. In fact, you can show that if you have this equation, then you can modify the product to pass to an equivalent product in the sense which I explained, so that the second term will look precisely like this. I'll talk about this a little later. So last time I gave you an example of the star product in the case where M and pi are given by the dual space of a Lie algebra and the standard Kirillov constant Suryo structure. In this case, we induce the star product using the Poisson-Hall theorem. That is to say, we induce this star product from the universal enveloping algebra. First, we do it on the space of polynomial functions on G check. We induce it from the universal enveloping. So this is linear isomorphism, in fact. And then we show that since this star product is given on this space of polynomial functions by some universal series of bidifferential operators, we extend it to all functions. In fact, if you work with symplectic manifolds, you can take advantage of the Darboux theorem. Which says that locally, for every point P in a symplectic manifold M, there exists an open neighborhood UP inside M, such that there exist coordinates on UP such that the symplectic form in these coordinates is equal to the standard symplectic form on Rn, R to n. Standard form on R to n. In particular, it means that in these coordinates, all coefficients of omega are constant. And hence, we can actually use Moyle product construction to define the star product in this UP. After this, we are left with the classical example of local to global problem in geometry. When you have some structure which is defined locally around every point in a manifold, then your problem is to globalize this structure. There are various constructions which allow you to do this, beginning with the partition of unity construction, including some constructions in sheaf theory, in sheaf cohomology, and so on and so forth. In any case, in symplectic case, this problem is local, is global, in fact. However, in Poisson case, in genuine Poisson case, we don't have Darboux theorem. There's no Darboux theorem. No Darboux theorem. Instead, we have Weinstein theorem. Which says, well, I don't know, I don't remember if I have actually explained this theorem at these lectures or not. I think I definitely mentioned it, especially at our seminars, but I didn't explain this theorem here. I'm not going to prove this theorem. It's pretty technical, but let me just formulate it. So for every manifold M with Poisson structure pi on it, they exist, and for every point P in M, they exist an open neighborhood UP of the point P inside M, such that UP is diffeomorphic to the product of, let me put it like this, open disk of dimension 2k cross S, where this dk, d2k, bears the standard symplectic structure, is equipped with the standard symplectic structure. in some coordinate system after this diffeomorphism. And S is equipped with some Poisson structure such that S restricted to the 0, to the origin. So S is also you can actually regard it as some neighborhood in R dim M minus 2K. So if you restrict S, so the Poisson structure on S restricted to the origin is equal to 0. So the Poisson structure just vanishes on S, just vanishes at 0. And we know nothing else about this Poisson structure on S. This is pretty poor classification, in fact. It just says that if the rank of pi at point P is equal to 2K, then locally pi is equal to some symplectic form of dimension 2K plus pi tilde, which vanishes identically at pi. There is no description of pi tilde. The only piece of information we can glean from this construction is that if rank of pi is constant all around M, or at least in some neighborhood of P, then in a neighborhood of P, one can introduce coordinates y1, y2k, z1, zn minus 2k, where n is dimension of M. Such that pi is equal to dy1 dy2 plus dy2k minus 1 dy2k, and that's all.
It's like the Darboux theorem?
Sorry?
It's like the Darboux theorem?
It's like Darboux theorem, but only when we know that the rank of pi is constant. If the rank of pi changes, and it usually does, and we have no control over the way it changes. And that's why if you want to conclude, for instance, the Lichnerovich-Poisson cohomology for a genuine Poisson structure, you are in big trouble. You can have, the computations can be pretty non-trivial. Whereas if you want to compute the Lichnerovich-Poisson cohomology for symplectic structure, you just end up with the Ram cohomology, which is very well known, very well studied, and it's usually finite dimensional. You can tell nothing like this about the genuine Poisson structure. You cannot even say that Lichnerovich-Poisson cohomology of a genuine Poisson structure is finite dimensional. Just take 0 Poisson structure, and the cohomology will be infinite dimensional. So that's always quite a big trouble. And so in order to study the generic case where we cannot hide behind the Darboux theorem and Moyle product, it is highly advisable to develop some general theory of deformations. So let me say a few words about deformation. I'm not going to give you the most general version of this deformation theory, because general version of deformation theory actually is quite well developed. There are a few very abstract notions, very abstract constructions there. So let me just stick to something very basic. So let A be an algebra, an associative algebra. We want to introduce a product, an associative product, an H-bar linear product in the space of formal power series A with variable H bar. So we need to find a formula A star B equal to, the first term is usually fixed to be A times B, the usual product in A. But then we add all the remaining correction terms from 1 to infinity. H bar to the power k times bk of AB. And these bk's are not, well, differential operators. Why differential operators? Because we don't know anything about bk. We don't know anything about A, so we cannot say what type of operators they are. The only thing we can assume that bk are bilinear over the ground ring. Because, of course, we want to preserve the structure of algebra. That is to say, if we want to take the product of some lambda A plus mu B with some C, we assume that it will be equal to lambda A star C plus mu B star C, and so on. Therefore, we should assume that these operators are bilinear. Okay. But we still have one condition to satisfy, even if we forget about the technical conditions 3 and 4, which are, of course, the same. Symmetricity and the fact that 1 is still the unit. We don't care about them. We don't care about the second term because we have no prescriptions as far as the second terms are concerned. But we can still ask for the associativity of the star product. So what does this associativity condition mean? It means that A star B star C is equal to A star B star C. And we can now expand this equation in parameter H bar, as physicists are, well, I think are acquainted with this method. That's what they call the, how do you call this? Perturbation, right? The perturbation series. Am I right? Is this the term? So when we take the 0 degree h to the power 0, that is no h at all, h bar at all, we just get the usual associativity condition for the usual product in A, which is by condition there. But when we turn to the first degree condition, we get something non-trivial already. So on the left, we'll get A times B1 of B comma C plus B1 of A, B, comma, C. And on the right, we will have B1 of A. I think I'm confusing the left. No, I'm not confusing. A, B. I confuse this one. A, comma, B, C. Sorry, I confused this. It was my slip of hand. Plus B1 of A, B times C. If we collect all the terms on one side, for instance on the left, we'll get this formula. So I think you're already quite familiar with cohomology. We discussed some cohomological constructions at our previous seminar a week ago. So you probably noticed that this looks very much like some cohomological formula, alternate sum of elements in the middle. So I'm going to develop this idea and introduce a cohomology theory which will take care of the formulas which appear in this associativity equation. Before I proceed, let me just formulate some meta principle, which is nowadays the common sense in the theory of deformations. The principle says that whatever deformation you consider, be it of some algebraic structure or some geometric structure, you will sooner or later come up with some cohomology complex which will regulate this deformation procedure. So in this case, in the case of deformations of associative algebras, this complex is well known. I think it appeared in 1940s for the first time. At that time, nobody actually expected that this complex will play such an important role in the deformation theory. And I think that the purpose of introducing this complex at that time was just to give another example of cohomology. And cohomology theory at that time was, developing rapidly. So the more examples people would find, the better it was. So let me now proceed with the definitions. Let A be an associative algebra. So I'm going to introduce both homology and cohomology simultaneously. Let M be an A bimodal. Let me recall that a vector space is called an A bimodal if it is endowed with two model structures, left model structure and the right model structure, which verify the standard set of equations. So it is, they are both associative on the left and on the right. And also verify the commutativity condition. The left action of A commutes with the right action of A. So if I call this left and this right, then you can take left here and up here. Then you take the right action, and this will be the same as this composition. Right. In this case, you can introduce the following chain and chain complexes. So let me begin with the chain complex. So left one will be the chain complex, which I'll denote by C dot A comma M. And in dimension K, this complex will be equal to the tensor product of M, which is traditionally written on the left, although of course you can write it on the right as well, due to the commutativity of tensor product, right? Of A and A taken K times. So I will abbreviate this to just M tensor A to the power K, to the tensor power K. In particular, when K is equal to 0, we have C0 AM equal just to M. In cochain complex, you should be a little bit careful here, because people usually assume that chain and cochain complexes are dual to each other, but this is not the case in the case of in the theory of Hochschild homology and cohomology. They are not quite dual unless you choose very carefully the bimodules on both sides. So in this case, CK AM is equal to the space of all homomorphisms from the tensor power of A, kth tensor power of A and M. So, by the way, whenever I write tensor product and space of homomorphism without any subscript or superscript, I assume that these operations are taken over the ground field, right? You should be aware that if I write something like I don't know, B, A, V, I assume that both A and V are B modules. So I consider all maps which intertwine the structural B modules on both sides. When I skip B from my notation, it means that I assume just linearity over the ground field, nothing else. Okay. In particular, again, if K is equal to 0, then C0 of AM is again equal just to M. Now I need to introduce the differential, which is the most important part of every complex, right? And in this case, the differential is given precisely by the formula which you would expect. So on in case of chain complexes, this differential is usually denoted by B. I think this is abbreviation from the boundary operation, boundary operator. And B applied to M tensor A1, tensor and so on, tensor AK is equal to the following sum. First we take M and multiply it from the right by A1, and then all the other terms show up in the usual order. Then we go on and take the alternate sum from I from 1 to K minus 1. So first of all, we take minus 1 to the power I. After this, we take M, take A1, and so on. Then we have AI plus 1. And we end up with AK. Right? But that's not all, because we need to add one more term. And this term is minus 1 to the power k, AK, M, tensor A1, AK minus 1. It's a good exercise to show that b square is equal to 0. Of course, I'm not going to do this in the most general situation, because as you see, we'll end up with quite a long combinatoric problem, quite tedious. But let me do this in some low dimensional case. For instance, let's take b k equal to, I don't know, 2. I think 2 is enough for us. First, we take b of m tensor a1, a2, and this is equal precisely to m a1 tensor a2 minus m tensor a1, a2 plus a2 tensor m, a2 m1, m tensor a2 a1. Now b square applied to the same element is equal to what? First we apply b to this term, and it looks like m a1 a2 minus a2 m a1. To this we subtract m a1 a2 and add a1 a2 m. After this we add a2 m a1, right, and subtract a1 a2 m. And all the terms, as you see, cancel out. For instance, this cancels out with this with this, and finally this with this. So it is equal to 0. In general situation, we have pretty much the same formula. There will be 3 causes of cancellation. I think actually 4. First of all, we'll have cancellations which appear due to the fact that we can take 2 products in this string of tensors in different places, and they show up with different signs, right? Then there will be cancellations which appear from the associativity of left and right actions. And finally, there will be cancellations due to the commutativity of left and right actions. All these elements will show up. Okay, the cohomology which obtain, the homology which obtained in this case is called the Hochschild homology. Hochschild. You see, it's pretty complicated German name. Right, Hochschild homology of A with coefficients in M and denoted by H dot A comma M. In some situations where M is equal to A, in many cases this is abbreviated to H dot of A. Of course, A is a bimodule over itself, and that's why we can always plug it in this construction. The differential in the cohomological case, in the cochain case, is pretty much the same. So in the cochain case, This differential is usually denoted by delta, although this notation delta is not as fixed as the notation of B for the homological case. Well, but in most books which I read, this differential in Hochschild cohomology is denoted by delta. So delta of phi. So phi, let phi be an element in Ck of A comma M, which is the space of all homomorphisms from A tensor K to M. So this will be a homomorphism from K plus 1 copies of A. And as you see, I just omit the tensor product sign. And in many situations, well, in most books, in most formulas, people do the same thing. People use commas because they are much shorter and much smaller than the tensor sign. So you see here we have K plus 1 argument, which we plug into delta of phi. So this now is equal to the following combination of elements. First, we take A0 outside, apply phi to A1 through AK, we obtain an element in M and multiply it by A0 on the left. After this, we proceed just like before with alternate sum of phi applied to the combination of AI plus 1, AK, but multiplied with minus 1 to the power I, right? And finally, we'll have minus 1 to the power K, phi A1 AK minus 1 multiplied by AK. Again, the condition that delta square of phi is equal to 0 is quite tedious. Let me do this for phi of, I don't know, of degree 1 again. So first, delta phi of A comma B is equal to A phi of B minus phi of AB plus phi of A times B. And delta square of phi applied to A, B, C is equal to the following. First, we take A delta phi of BC minus delta phi of A, B, comma C plus delta phi of A, comma BC and minus delta phi of A, B times C. By the way, if you look attentively, you'll see that the formula on the right is precisely for the associativity condition where we replace B1 by delta phi. It is precisely this condition. Okay. So let me proceed with this formula. So instead of delta phi of BC and everything, I'll plug in these formulas. So what do I get? A times B phi of C minus A times phi of BC plus A times phi of B times C. That's the first term. Now we have minus delta of AB C. That is AB phi of C plus phi of ABC minus phi of AB times C. And we have plus phi of what? ABC. Oh, is it phi? Sorry. Oh, no, it's correct. It's incorrect. Phi, A times phi of BC. Right? Minus phi of ABC plus phi of ABC. And finally, what we have is minus A phi of B C plus phi of AB times C minus phi of A dC. So let us look attentively and see that everything is cancelled out. For instance, this term cancels out with this term, this term with this term, this term. Why do I have this C on the right with this term? Then we have these A, B, C, and this. We have, I think I'm running out of signs, right? With this. And the last one, but not the least, is this and these and this and these two. So they always cancel out again. And it's a good exercise for everyone to check this in the generic case. And the cancellations will be due to the same reasons. First of all, to the associativity of left and right action, to the commutativity of products inside the string. So if you have two products and they take them in opposite, in different places, then you can take the first one and then the second one and do the opposite, and you'll get opposite signs. And finally, they'll appear from the associativity of product in the algebra itself. Okay, so in any case, we have the cohomology, and again, the notation is the standard one. The cohomology of this complex is called the Hochschild cohomology of A with coefficients in M. And if A is equal to M, then we just write H dot of A. I think it's a good thing to give an example. There will be more examples in your exercises. Take a look there. I'll give probably the simplest one. Simplest one is when A is equal to the algebra, to the ground ring, ground field itself, right? Then you take a tensor product over the ground field. A tensor A of the ground field itself, you get a ground field in the end, nothing else, right? So it means that the complex C dot CK A comma M, in this case, M is any vector space over K. Okay, will be equal to M in all dimensions. Now the question is to describe the differential. So what is differential B from, say, M tensor 1 to M? It is equal to M minus M, that's 0, right? If we take B from M tensor 1 to M tensor K, right? All the elements in this tensor product can be written like this, yeah? Because the unique generator of K over K is just the unit. So we can write any element in this form. And in this case, the differential will look like M tensor 1 minus M tensor 1 plus m tensor 1. In other words, it is equal to m tensor 1, right? So we can now write down, I think by induction, or you can prove it directly, that the differentials here will look like identity. So this is 0 dimension, k dimension, this is identity. So this is 0, right? This is 1 dimension 1. So this is dimension 1 to dimension 0 is 0. Here we have identity. Here we have 0 and so on. And this actually pretty well matches with the fact that b squares to 0, right? Since b squares to 0, of course this is also always equal to the composition of any two elements here is equal to 0 all the time. The cohomology in this case is pretty evident. You see that the homology is direction 0 in dimension 0 is equal to m, right? Because there is nothing on the left here. Everything goes to 0, right? And there is no, so every element here is closed, but there is nothing exact in M because the image of this map is equal to 0. So
We can say that we obtain short exact sequence.
it's actually just a very simple. I wouldn't like to use this, nice words for this simple situation, to describe this simple situation. However, if in high dimensions, the cohomology is always equal to 0. And that's why. So if k is odd, then as you see, everything is in the kernel of the boundary map, right? But on the other hand, everything is also in the image of the boundary map. So the quotient is equal to 0. And if k is even, then the kernel of the boundary map is equal to 0. So there is nothing to think about, right? And we have this. So that's the simplest example. In general case, the computations are not that easy, of course. And if you try to do this by definition, you end up with pretty hard computational problems. Sometimes, though, well, in low dimensions, you can overcome the difficulties and describe somehow the space of cohomology in some nice terms. For instance, if k is equal to 0, then for every and m, what do we have? We have the following. The kernel of B from C0 AM to C minus 1 of AM, which is 0 and which is M. This one is M, is equal to M, nothing else. And the image of M from C1 AM to C0, which is just M, is equal to the following, to the space of commutators. Namely, what is, sorry, not M, V. This map is given by the following formula, right? If you take M tensor A, then its image is equal to MA minus AM, which you can abbreviate to the commutator of M and A. So the image is equal to the space of all commutators of this sort, or more accurately, the space generated by all the commutators. So H0 in this case of AM is equal to the quotient of M modular the space of commutators. And sometimes, so this space is sometimes called the space of universal traces or something like that. There are some special abbreviations, but of course, the actual size of the space depends on depends very much on the way the product in M is done, right? For instance, if AM is always equal to MA, then H0 of AM is equal just to M. If we do the if you try to do the same thing with in degree 1, it will not already be that easy. It's not very hard to describe the kernel of the boundary map from C1 to C0. But describing the image of the boundary map from C2 to C1 can be quite tricky. So I'm not going to do it like right now. I'll probably speak about this a bit later in some particular cases. Let us instead consider the dual situation. So if A is equal to K, let us now compute the cohomology H dot of AM. Let's do the same construction. So CK of A comma M in this case will be equal to M again, right? And the boundary is a bit more tricky again. For instance, delta phi, so in degree 0, what do we have in degree 0? So in this case, phi 0. We'll get an element which will depend on some element 1 in A, and it will be equal to, so phi 0 is an element in M. It will be equal to M minus M. So delta is always, delta of phi 0 is equal to 0. Delta of phi 1, again of 1, 1, what is it equal to? It is equal to M. So let me, phi 1 of 1 is equal to M. Yeah? In this case, what do we have? Is equal to, it is M, right? Minus M and plus M again. So it's again equal to M. And in general, we'll get the same picture as before. We get a chain of M's and a chain of maps interchanging identity and 0 at every stage. So again, the cohomology of K with coefficients in M is equal to M if the degree is equal to 0, and in all other cases, for the same reason, it is equal to 0. In this case, you can also say something about, in the case of cohomology, you can say something about the structure of cohomology in lower dimensions in the generic case. For instance, H0 of A with coefficients in M. What is this? So C0 in this case, in all cases, is equal to M, as I explained. The differential from C0 to C1 will send every element M here to delta of M, which is a map from A to M, right? Delta of M applied to A is equal to AM minus MA. So M is in the kernel of delta if and only if M commutes with every element A in A. Right? So such elements are usually called the center of the bimodal. The center of bimodal. And of course, since there are no exact elements in C0, we conclude that H0 of AM is equal to, well, this center is sometimes denoted by, I think, M sharp or something like that. A space of elements which commute with everything in A. In particular, if A is equal to M, this is just the usual center of the algebra. In this case, we can even say something about the structure of H1 of AM. Now let us consider an element phi in C1 of AM, which is just the space of all homomorphisms from A into M. And then delta of phi is equal to 0 if and only if for all A and B we have the following equation: A phi of B minus phi of AB plus phi of A times B is equal to 0. Right? So we conclude that phi is in the kernel of delta if and only if phi of AB is equal to A phi of B plus phi of A times B. And that's precisely the Leibniz rule in the non-commutative sense. Because in the commutative sense, in commutative case, you can write both A and B on the left. And that's how you usually do this in analysis, in the calculus. But in non-commutative case, you should distinguish the left and right product. If you have ever tried to differentiate matrix products, the products of matrices, you'll see that you get the same formula here. So we see that the kernel consists of all derivations. The map which verifies Leibniz rule is called derivation from A to M. So phi is a derivation A to M. And the space of derivations is usually noted by der of A, M. Sometimes if we assume that the maps are linear over some algebra B, people add B here, but here this algebra is equal to the ground field, so people usually omit it. We go on. That's not yet the cohomology. because in order to obtain cohomology, we need to quotient out the space of exact forms, right? So what are exact elements? As I already explained, phi, which is in C1 of AM, is in the image of delta from C0 AM to C1 of AM, if and only if phi is a linear combination of elements of the form A, phi of A, phi m of A is equal to AM minus MA, where M is some element in M. Of course, every element of this form verifies Leibniz rule. This follows from the properties of commutators, and also it follows from the fact that the differential delta squares to 0, right? So phi sub m of A, phi sub m is always a derivation. In order to distinguish this particular case of derivations from the generic derivations, people call these derivations inner derivations. So we conclude that the first cohomology of A with coefficients in M is equal to the space, the quotient of the space of all derivations of A with coefficients in M, modulo the space of inner derivations of A with coefficients in M. This space is sometimes called the space of outer derivations of A, comma M. In many situations, this space of derivations can be easily described. For instance, if A is equal to the algebra of polynomials with n variables, right? Then, of course, all inner derivations.
The inner derivations were the ones that come from commutators.
Yeah, precisely. In this case, all inner derivations are, and M is equal to A. Yeah, let me consider this particular case. So in this case, all inner derivations are equal to 0 because of the commutativity of A, right? And we conclude that H1 of A comma M is equal to the space of derivations of this free commutative algebra with n variables, which is, of course, given by every derivation of this sort is given uniquely by the value of this derivation on every variable. If we know the value of this derivation at every variable, we know the value of the derivation at every polynomial. So if some derivation x sends variable x1 to some polynomial p sub x of x1 through xn, right? And we see that every derivation is uniquely determined by precisely n polynomials. And we conclude that this space is isomorphic to the tensor product of the algebra of polynomials. With the space of variables. How do you denote it? Maybe just, let it be just K n, just this. Okay? In general, you can consider the following construction. Let T K of K x1 T poly xn be equal to the tensor product of this algebra with the wedge product, the kth wedge product of Kn. Roughly speaking, this is just the space of polynomial of polyvectors in n variables with polynomial coefficients. K polyvectors with polynomial coefficients. Polyvectors on Kn. So we can regard this any element here as the combination of certain polynomials I1, Ik, where I1, Ik from 1 to n. Dx1, dxn, ddxi1, ddxik, of course. Right? And these are some polynomials. And we can consider the map, which I denote by chi, and that's what we call the Hochschild constant Rosenberg map in this particular case. From this space to Ck of A, comma A. So A is for me, as before, the polynomial algebra. The map is given by, if you take the polyvector P and apply it to elements A1 through AK, and you just take the usual thing. You take this polyvector and pair it with, D1, DAK with differential form. My purpose is to prove that this map induces isomorphism in cohomology. Moreover, I'll do this in the case of algebra of functions on some smooth manifold. But I think today it is worth to speak a little bit about the algebraic case. The algebraic case means the algebra of polynomials. Because of course when you speak about the algebra of smooth functions, this algebra is huge. You have even to modify the very definition of Hochschild homology and cohomology for everything to work properly. So let us first consider the case of polynomial algebras and the case of usual Hochschild homology and cohomology. So let's speak about first of all, I'm going to speak about some dual map gain. Oh, sorry. And I define a space of K forms on A to be equal to the tensor product again of A with kth exterior power of Kn. Roughly speaking, it is a space of all formal sums A, I1, I, K with the same set of indices. Of x, some polynomials, times dxi1, dxin. I'm not going to introduce the theorem differential here. So for me, it is just the set of formal expressions of this sort. Just the space of this form.
We have a little question here on the polyvectors. What is the cohomology? Or the idea is to do this, to compare this with the...
No, the claim is that this map, on the left I have no differential, whereas on the right I have some differential.
I see.
The claim is that if I send this map to the right, then this map will induce the isomorphism cohomology. When you have no differential, you can say that you have zero differential.
Okay.
So in other words, this claim means that the left-hand side is equal to the cohomology of the right-hand side. Okay. And I have a map from Ck of A comma A to omega k of A. So this map is given by the following. We have the element here is of the form A0 times A1 times AK. And these A's play different roles. This A0 plays the role of the element in the bimodal. And this A1 through AK, they play the role of elements in A. And hence I have some separate meaning for these elements, and this justifies the following map, which is also called the Hochschild-Kosten-Rosenberg map. It sends this set to the following element in omega k, namely to A0 d A1 d AK, where d is taken in the usual sense, which you are familiar with. Everything here is a polynomial. So when you take the usual theorem differential, you get some element in omega 1, and you take the wedge product in the usual sense, right? And again, Hochschild-Kosten-Rosenberg says, Hochschild-Kosten-Rosenberg theorem, this map is an isomorphism in cohomology, in homology. So I'm going to if not prove it today, then at least to start the process. I think it is worth to distinguish algebraic and smooth case, because the methods you use in algebraic case are different from the methods and more universal than the methods you use in smooth case. The algebraic case will give us the opportunity to speak about some properties of homology theories. So let me give you some, make a digression about the homology, the general homology and cohomology theory of rings and algebras. Let A be an algebra M, it's right A by module. We will say that M is projective if well, there are two equivalent ways to formulate it. I begin with some more explicit. If M is a submodule in a free A module with I probably better to formulate like this. It is split submodule in a free A module. So what does it mean? It means that they exist some natural n and some other right A module n such that A, if you take it in quantity n, so if you take n copies of A, and you have a splitting of this direct sum into M and n. This is the very more or less explicit way to define projective models. There is another way to define projective models by the universal properties. Here they are. So an element, an A module M is called projective if for every diagram M into N, here we have an epimorphic map P. So for every map M into N, M is any A module and here we also have any A module. And here we have an epimorphic map there exists a map I from M to P, which makes this diagram commute. I quite forgot to say that also we assume that M is finitely generated. And M is finitely generated. Sometimes people actually distinguish between just projective modules and finitely generated projective modules. So if you want, you can actually add here that M is finitely generated projective if this. And they also we'll put it here. But then you need to add this condition. Okay? So for all the modules for me will be finitely generated, so I'll not distinguish between the two notions. But if you run into this in some book, you should should remember that the condition of finitely generated, of finite generations, I don't know how to say it in English, finite generatedness, something like this. It sounds awful. Is necessary. Let us briefly show that these two notions are in fact the same. So for instance, if M is equal to some submodule of the direct sum of this free module, right? What do we do? For every diagram of this sort, oh, that's different n. Let's put Q. Let's put Q here. P and Q. We extend this to the map A n onto M, projecting it along n. And then here, right? This gives us, for every generator here, we have some element. So let's write down this composition. I don't care about this. So for every element E, I, generator of A, N, we have composition of these two maps in Q. And since this projection is epimorphic, there exists some element epsilon I in P which projects into it. Let it be pi. So I sent now this element to E by EI by J, by some map J to epsilon I, right? And this diagram is commutative now. And then to make the whole diagram commutative for M, I take the inverse map, the injection of M into this direct sum I don't know, I capital. So I is equal to the composition of J and I capital. So this gives you the desired map from here to here. And vice versa. If we can take the diagram M into itself. And here we take the free module spanned by the generators. So if M is finally generated, so we choose the generators and span the free module by the elements indexed by the generators. Right? This is, of course, epimorphic. So by the universal property on the left side of the blackboard, I have this injection. Right? And it means, since we have, so the composition of this injection and this projection pi is identity. And hence the kernel of pi forms direct sum with the image of M, of I. So we just identify the image of M and M itself. And the kernel is the second model we need. So these two notions are equivalent. And the importance of this projective condition is that it allows you to construct maps by inducing maps from, so if you have some epimorphic map and you have some projective module mapping into the image of this epimorphic map, then you can raise this map from M to the source of this epimorphic map. So now by the way, how much time do I have?
-5.
Oh, I'm sorry. So next time probably minus 16 minutes. That's too much. Yeah, since I got later here, I think, yeah, it's okay, but still I think it's better to because it will take me at least half an hour to conclude. So I'll probably start with it next time. So we'll start next time. I'll go into some homological algebra. I'll speak about projective resolutions, and I'll describe our Hochschild homology and cohomology as some derived functors in the sense of homological algebra. And that will allow us to compute certain examples with more ease than it would take us if we were to compute them by definition. Okay, that's all.